Hello and welcome back to the course on deep learning. Today we're talking about energy-based models. And this topic is one that is not really necessary for you to be able to apply Boltzmann machines. So we could have just completely not talked about energy-based models and you would have been totally fine. You would have been able to understand them on an intuitive level and also to apply them in practice. But at the same time, if you're going to delve into the space of deep learning and specifically the more advanced things like Boltzmann machines, you're inevitably going to come across the term energy-based models. And we wanted to make sure that you're comfortable with it. And plus, it'll give you that extra level of understanding, of intuitive understanding of where things are coming from and how exactly to think about the Boltzmann machines and these stochastic processes that describe systems. So let's have a look. Here we've got an equation. And by the way, have you wondered why it's called the Boltzmann machine? Well, the reason is because of this equation. This is the Boltzmann distribution. It comes from physics, and it is used in the sampling distribution for the Boltzmann machine. You know how the Boltzmann machine constantly creates these different states of our system? Well, in a very rough description, it's using the Boltzmann distribution as part of that process. And the Boltzmann distribution talks about probability. So on the left, we've got a probability. And I know this formula might look a bit complex right now, but as we go through it, you'll see that it's very simple. And then we'll look at an example of how it actually works in real life. So we've got a probability here, and this is the probability of a certain state of your system. So we're describing the different states of our system. I is a state. This is the probability of your system being in state I. And probability of your system being in state I is equal to E as an exponent to the power of minus energy of that system divided by KT. K is a constant and T is the temperature of your system. And then divided by the sum of all of those values for all of the possible states of the system. So it's a pretty straightforward formula when you think about it. The important thing here to see is that E is to the power of minus energy, meaning that the higher the energy of a certain state, the lower the probability. So probability is inversely related with energy. And so we're kind of like assuming that the temperature, we're looking at a system at a given temperature. And this is for thermodynamics. So in a thermodynamical system, so for instance, a gas, or it could be any kind of system, right? It could be it can be a macro system like a gas in a bottle or in a room. It could be a micro system. It could be just some molecules together or just one molecule. But in any case, the probability of your system being in a certain state is inversely related to the energy of your system in that state, right? And so let's have a look at an example to explain this a bit better. Let's say we have a room. This is probably one of my favorite examples. And you've probably even heard this example back in high school. Here we've got a room, and here we have, let's say, some people, and then we've got a gas, for instance, air. So have you ever thought of why the gas is distributed across the whole room? Why is the gas, for instance, not all in one corner? Because that could technically, there's nothing preventing that from happening, right? The molecules of gas, there's nothing saying that they have to be there. They have to be all over the room. They could be anywhere. They're moving around, and statistically, they could end up here. This could happen in any room at any given point in time. This is a example of a possible state of this system. All of the molecules, for instance, in the room you're sitting in right now, they could just decide to go all into one corner, or statistically they could end up in that corner. But what the Boltzmann distribution is saying, that the probability of that state occurring is very low because the energy in that state would be very high, because the molecules would be very close to each other. They would be bumping, they would be making a lot of chaos and havoc, and they would be moving very quickly. To be in that state, they would have to have a huge energy. Given the same temperature of the room, temperature hasn't changed, but the molecules would have to have a lot of energy if they were going to be in that state. And the probability is very low. And so basically it's a translation into the language of statistics saying that, hey, this could happen. Probability is tiny. And what we normally observe is this, because this is the lowest energy state for that system when the molecules are like equally spaced apart. They're just moving around. Yes, they're bumping occasionally, but there's no, if there were an even lower state of the system possible, then the system would eventually, with the highest likelihood, end up in that state. But this is already the lowest energy state for the system possible, and therefore that's what it is. And that's why, for instance, we can move around and breathe and enjoy our lives as we are without having to worry about situations like this. So there we go. That's a quick example of the Boltzmann distribution in real life, and it applies to everything. For instance, if you drop some ink into water, it will start spreading evenly in all directions. It won't form a star, for instance. It could form a star or a snowflake, but it's not going to, because that's not the lowest energy state. On the other hand, if you put a drop of oil into water, then it won't start spreading. It will turn into a little ball on the surface of the water, because that is the lowest energy state for that specific system. It happens everywhere through life, and Boltzmann machines are constructed with a similar concept in mind. So energy is defined in Boltzmann machines through the weights of the synapses. And then once the system is trained up, once the weights are set, then what happens is the system, based on those weights, will always try to find the lowest energy state for itself. So it has lots of different options, just like a gas in a room. It has lots of different options. It can be in this state, it can be in that state, but the weights will dictate what is the lowest energy state for the system, and it will constantly try to get to the lowest energy state possible. And that's how it works, and that's why they're called energy-based models. And here's an example of an energy function for a restricted Boltzmann machine. We haven't talked about them yet, but we'll discuss them in the upcoming tutorial. Here I just wanted to point out that what it would look like. It's a bit different to the case of the Boltzmann machine energy, or the Boltzmann distribution energy, because it's not a gas. But at the same time, you can see that it is defined through the weight. So A, B are biases in the system, so just constants. V and H that's a visible node that you're looking at. Specifically, you're calculating your equation. H is the hidden node that you're calculating. That's your visible node again. That's your hidden node, and that's the weight between the visible and the hidden node. And so, as you can see, your biases are fixed and your weights are fixed here. And then the system knows that its energy function will be determined in this way. And then the probability of being in a certain state is given through the energy, just like in the Boltzmann distribution, where Z is the sum of all of these values for all of the possible states, just like in the Boltzmann distribution. And so from that, we know that the probability of being in a certain state is inversely related with the energy of that state. And the system also knows that, so it's going to play by those rules. It's going to find the lowest energy state just because of the way we set it up. So that's a very high-level overview of energy-based models and why they're called Boltzmann machines, why this specific model is called a Boltzmann machine, and how energy plays in the functioning of a Boltzmann machine. It's very different. This whole concept is very different to what we had in just neural networks. And if you'd like to learn more, there's a great article, or there's a great paper actually, an article by Yann LeCun from 2006. It's called A Tutorial on Energy-Based Learning. And it's very long. I think it's like 50 pages long or something. So if you really want to dig in to energy-based learning and energy-based models, then this is probably the best place to start. If you don't have time to read an article or to read a paper, and you'd just like to get a bit more of a good feel for all of these things like entropy, and this concept of energy and entropy and Boltzmann distribution, they actually are very closely tied to how we live our lives. For instance, why does time travel forwards and not backwards? And why if you mix two liquids together, if you mix two liquids together, you can't then unmix them. Why smoke goes out of a cigarette, not back into a cigarette? Why you can remember the past and you can't remember the future? These kind of very philosophical questions. We're getting very close to that when we're talking about energy-based models and things like entropy, even though we didn't really mention entropy throughout this tutorial. But if you'd like to get into a bit more of that without having to read a paper and understand mathematics and all of these things that govern that, it's a great movie that I can recommend you. It's called Mr. Nobody by Jacques van der Mel, created in 2009. It's got Jared Leto. Great movie on all of these things, on entropy, on how time travels forwards and things like that. It was premiered at the 66th Venice International Film Festival. So if you're looking for a good movie, I would highly recommend checking this one out. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.